Welcome again to Analytic Methods for Lawyers. Today we're going to be talking about the p-value, one of the most important concepts in traditional frequentist statistics and definitely one of the most poorly understood. There are many papers, in fact, investigating just how poorly even educated people are in understanding the p-value. And some people might say it's not that important because people shouldn't be looking at p-values, but the fact of the matter is people still do look at p-values a lot, and therefore it's important that you understand it. So the goal of this essay or this video is to make sure you know what a p-value is, that you're able to spot misunderstandings about what a p-value is, and also that you understand the difference between a one-sided p-value and a two-sided p-value. Okay, so let's talk about the definition. It's, as I said, it's a slippery concept, and it's one of those things that you just need to commit to memory. The first thing to remember is that there are no p-values in the air. You can't just look around and find a p-value. A p-value is attached to a statistic and to a test, and that test may only be legitimate under certain circumstances. So if the test is illegitimate, the p-value is illegitimate as well. I'm going to say that again. The p-value is attached to a statistic and to a test. The test may be legitimate under only certain circumstances, and the p-value is only as good as the statistic with which it is associated. I'll let you read it the third time, but let it sink in. You should make sure you understand there are one-sided p-values and two-sided p-values. Okay, it makes a difference which you are using, and there are circumstances in which use of a one-sided p-value really doesn't make much sense. There are circumstances in which use of a two-sided p-value doesn't make much sense, and there are cases in which you might want to use either. So you need to understand why the person has chosen to use a one-sided or two-sided p-value. Okay, so what is it? It's a kind of a meta-statistic, and what you're going to do is determine the distribution of some statistic under a null hypothesis. We talked about this in a prior video where you figure out what some statistic would be if the null hypothesis were true, what the distribution of that statistic would be. That statistic is known as the test, and that distribution, not the underlying distribution, but the distribution of the statistic, we'll call script P. That distribution has a CDF, has a survival function, probably has a PDF too, but you're creating a distribution. What you then want to do is to determine that same statistic on your own data. And for now, we'll call that value delta. Okay? So let's go through it just one more time. You figure out a null hypothesis. You figure out what the distribution of some statistic would be if that null hypothesis were true, and then you figure out that same statistic on your own data. Now, let's talk about the one-sided p-value, which unfortunately there are two flavors. One is less common. There's an upper-tailed test and a lower-tailed test. And today I'm only going to be talking about the upper-tailed one-sided p-value, as these are considerably more common. All right, a one-sided upper-tailed p-value is the survival function of p, the sampling distribution of the statistic if the null hypothesis were true, evaluated at delta, the statistic on your own data. So I've written that in Wolfram Language here, and now let's take an example. Supposing we have a list of three numbers that we think they come from N01, not positive, but that's the null hypothesis. The test statistic is the mean of the squared values of the list. So let's figure out what the distribution of that statistic is. And we don't need to do an experiment here to do that. We could, but let's do it exactly. And the way we're going to do it is we're going to say, look, we have three normal distributions, x, y, and z. And we're going to take the sum of the squares of draws from that. And you remember in a prior video we discussed what the power total resource function does. It basically, in this form, takes the sum of the squares of whatever this list is. So we're going to get a transform distribution, which is the sum of the squares of three numbers drawn from three identical normal distributions. So there it is. And Wolfram Language is smart enough to know, oh wait, that transform has a name. That is a chi-square distribution with 3 degrees of freedom. And we could take a look at what this distribution looks like. Let's plot out the PDF of it. Okay. We could plot out the the survival function of it. Let's just change this code here. That's what the survival function looks like. And now, let's suppose the 3 numbers in our data are 1.1, 1.2, and negative 1.4. So let's compute that same statistic, the sum of the squares, on our data. All right, 4.61. And so now what we want to do is to see where does 4.61 fall on the survival function of our test statistic. And so you can see, there's our 4.61, there's the survival function of our test statistic, and you can see it falls at about 0.2. And so this means that you haven't really disproven the null hypothesis, because even if the null hypothesis were true, you could get a sum of squares for your data that was at least 4.61 about 20% of the time. And usually we don't think that that's enough to reject the null hypothesis. We can talk about whether that use of a 95% confidence really makes much sense and the circumstances under which it might not, but traditionally speaking, you're going to want to see something less than 0.20, conversely greater than 0.80 for the survival function. Okay? So we figured out what our test statistic would be. I'm not saying this was a particularly good test statistic, I'm just saying it's one that we picked. We calculated a survival function, and we calculated what our statistic was for our own data. And from that, we made a conclusion that we can't really disprove the null hypothesis that this data is drawn from N01. Okay? All right. So what's a two-sided p-value? A two-sided p-value is fully appropriate if and only if the PDF of P, that sampling distribution, is symmetric about some value mu, which is usually the mean of the distribution. And so you can see why we wouldn't want to use a two-sided p-value here in general. There's no vertical line I can draw here in which the stuff to the left is going to be symmetric to the stuff to the right. I'm never going to get a mirror image by drawing a vertical line with this distribution. And so it's most likely inappropriate for a two-sided p-value. Okay? So, where the distribution P is not only symmetric, but it's unimodal, that is, it only has one hump, then there's a very simple, just as we used survival function for the one-sided p-value, we're going to use rarer probability for a two-sided p-value. Footnote, here's a distribution that is symmetric. You see, it mirror reflects around that line, but it's not unimodal, and therefore things get a little more complicated. But usually people don't design the statistic in a way such that it's bimodal. Usually if they're going to want to use a two-sided p-value, they're going to get you a symmetric unimodal distribution to begin with. So the more general algorithm for a two-sided p-value is set forth here, but really for almost all instances you're going to be using rarer probability. What you're going to be asking is, what fraction of the time would a draw from the sampling distribution be less common than the draw that I've gotten in my own data? Here's an example. Suppose we have reason to believe that if the null hypothesis were correct, a certain statistic would be distributed according to a student t-distribution with 3 degrees of freedom. Okay? I'm not going to tell you why that's the case, just assume it's true. Now we find that when we calculate that statistic on our own data, it has a value of 1.74. Let's see if that value disproves a null hypothesis. Okay? So what we're going to do is we're going to look at the PDF of the student t-distribution with 3 degrees of freedom, and then we're going to superimpose on that a dashed line that is at 1.74. All right, so there we are. Here's how our statistic is distributed, and here's where we are. Okay, now, let's actually shade the area to the right of that dashed line. Okay? We've shaded the area to the right of that dashed line, and with a little math, what we can find out is that that area is 0.09. And so that area is not less than a traditional significance level, usually called alpha, and a standard alpha is 0.05. And so we might say that we haven't disproven the null hypothesis if we're going to be using a one-sided p-value. But, gosh, that distribution kind of looks symmetric, doesn't it? Maybe a two-sided p-value is appropriate. First of all, let's just see if it's symmetric. What I'm going to see is it true? I say the line of symmetry is at 0. So is it true that the PDF evaluated at x is the same as the PDF evaluated at negative x? If that's true, then we've got a symmetric situation and we can use a two-sided p-value. It is true. So now let's look at a different picture. Okay? Here, what we could ask is on how many occasions would the probability of the statistic we get be less than or equal to the PDF of the statistic that we got. And so it's less here in this blue shaded area, and it's less here in this pink shaded area. And so if we add it up, that's about 0.18. And so if we're looking for a 0.05 level of significance, a statistic of 1.74 isn't big enough to disprove the null hypothesis using a two-sided p-value. Let's take another example. Supposing you're told that a certain statistic on data should have a chi-square distribution with 7 degrees of freedom, and you're told that your value for tau, your chi-square value, is 15.51. You've sort of registered in advance that you're looking for a p-value of 0.05 or less, and you now want to figure out, is your data statistically significant? Is it enough to disprove the null hypothesis? So let's again look at a plot of the PDF of the chi-square distribution with 7 degrees of freedom, and we'll superimpose on that a little line that's where x is equal to 15.51. Okay, so what do we see? First of all, we see that this is not a symmetric distribution. Therefore, use of a two-sided p-value is almost certainly inappropriate. And what we need to find out is how big is this area? If this area is like 0.01, well, then we could say that this makes the null hypothesis extremely unlikely. If it's 0.13, we could say, well, we haven't really disproven it with adequate strength. So let's do this. And if we do the math, it's going to turn out that this area is 0.02999, etc. So it's under 0.05. And by the way, another way we could do this without diagrams is just to say, what is the survival function of a chi-square distribution with 7 degrees of freedom evaluated at 15.51? And if all goes well, this should turn out to be that 0.0299 number, and lo and behold, it is. Okay, so there's a digression here on why people often look at means, and it's because the mean is a very powerful statistic. Okay, but what I want you to take away from this is what a p-value is. A p-value is the probability that you would see a test statistic as extreme as the one you do if the null hypothesis were true. And if that p-value is low enough, 2%, 1%, 1/10 of 1%, you might say that you have disproven the null hypothesis, or at least you've established that it's extremely unlikely that the null hypothesis is true. You can never be 100% sure. It's always a 1 in a trillion chance that just through random chance you got a test statistic that's quite extreme, but most of the time that won't be the case. So let's remember a few things about the p-value. The p-value is not the probability that the null hypothesis is true. It is not the probability that the null hypothesis is true. A result does not have a p-value. A statistic computed from the result may have a p-value, so long as you can compute a CDF survival function and usually a PDF for the distribution of that statistic. A low p-value doesn't disprove the null hypothesis. It means that under certain circumstances, the probability of the results observed and the null hypothesis both being true are low. And when we discuss p-value hacking, we're going to see how you can kind of depress a p-value to make it look significant when in fact it really is not. And so, again, you need to be very careful when people say, oh, I got a low p-value, therefore I disproved the null hypothesis. You need to know a lot more about exactly what they did in order to have confidence that that's actually correct. A higher p-value does not mean it's more likely that the null hypothesis is true. And finally, a p-value is only as good as the underlying statistic. If you're using an underpowered statistic, you might get a higher p-value than you would get if you used a more powerful statistic. And so one way to rig p-values is to use underpowered statistics. So when someone says, well, the p-value wasn't low enough for me to say much, you need to be asking, what statistic were you using? How do you know that that's the most powerful statistic around? Okay, that concludes our introduction to the p-value. It is something that you need to know. We will see it again in the course in regression and elsewhere.